Hello, Team Mountaineers from West Virginia University is excited to introduce our newest rover, Deimos, and our drone Phobos.
Deimos consists of two riveted sheet metal chassis connected together by a rotating center bearing. The center bearing helps Deimos maintain 4 points of ground contact when traversing a variety of different terrains. The 20-inch diameter wheel legs, or WEGs, on Deimos are comprised of in-house composite footers that are attached by an aluminum hub. The composite footers, made up of carbon fiber and Kevlar, are coupled with a unique tread design that help increase traction and reliability of the WEGs. The WEGs are attached to the two chassis through the use of motor pods, which serve to increase the ground clearance while also lowering the center of gravity of the rover. The compact design of Deimos seamlessly fits within size restraints without limiting functionality. The antenna mast assembly, reaching around 3 meters at full extension, seamlessly collapses into the chassis to stay within size restraints. Additionally, as opposed to the previous year's design, the front chassis of Deimos houses both the manipulation and science payloads, ensuring mission readiness within minutes.
Like past years, Deimos features a 5 degree of freedom palletizer-style robotic manipulator mounted on a horizontal linear rail. Thanks to the 4-bar mechanism, the arm is able to lift well over 10 kilograms while also minimizing motor torque. We have updated the arm to be composed entirely of My Actuator brand motors, which run on a CAN protocol to allow for better wire management. The redesigned end effector is able to grasp objects up to 14 centimeters wide. Its deformable grippers improve grip on objects, and our force sensing capabilities enhance operator feedback. The end effector has an embedded linear actuator for precise probing and a wrist-mounted USB-C for data transmission. This year's manipulator also features a swappable end effector so that we can tailor a specific system for certain missions.
For the science mission, we implemented a new end effector that collects both surface and subsurface soil. This rotating drum is designed to collect samples from 2 locations, using separate cutting edges and internal storage to reduce the chance of cross-contamination. Soil is then funneled into reservoirs filled with water, mixed, and transported to a rotating carousel of cuvettes using peristaltic pumps.
4 cuvettes are used for each sample site, 1 for a control sample and 3 for colorimetric assays. These tests, which are used to analyze if extinct or extant life is present, will be analyzed using a visual camera and a UV-vis spectrometer. To begin, spectral data is collected for the control solution to determine if organic material is present. Risazurin, ninhydrin, and methylene blue are in separate reagent cuvettes and will change color in response to metabolizing compounds, amino compounds, and oxidizing salts respectively.
After analyzing the surface sample, we then use the rotating drum to collect our subsurface sample. This is stored in a 2-part cache system consisting of a topsoil and subsoil cache. Additionally, we now collect the ambient environmental conditions at each site, as well as inside the rover, to support the results of our testing.
This year's rover uses 2.4 GHz with a 70 cm backup for general use in long-range missions, while 5.8 GHz is used for close-range, high-noise environments.
Deimos has 2 custom-printed circuit boards. The payload PCB handles DC motors and reads signals from sensors, and the power distribution board handles voltage regulation and provides e-stop functionality. Deimos has 2 40-volt batteries which can be swapped without halting rover operations.
Deimos traverses to waypoints using a multi-layered autonomy stack. This architecture allows switching between navigation algorithms to gracefully degrade if unexpected issues arise during the mission. The stack enables operators to generate paths using manual inputs, an A-star global planner, or a custom search algorithm using terrain cost maps created from USGS elevation data. During traversal, Deimos maintains localization through GPS data, supplemented by SLAM via IMU and LiDAR sensors for drift correction and loop closure to maintain global consistency. In addition, the LiDAR enables real-time terrain analysis to identify local hazards with a traversability score that fuses slope and surface roughness metrics. This local terrain map works in conjunction with Dynamic Window Approach, a local planner which provides real-time obstacle avoidance. If a safe path cannot be found, Deimos autonomously backtracks to a previously verified safe location. Aruto markers are detected using the OpenCV library, while objects such as mallets, rock hammers, and water bottles are identified using a custom-trained YOLO V12 model with integrated position estimation. If an Aruto marker or object is detected, Deimos transitions into a visual servoing mode, using camera-based pose estimation to guide the rover to within 2 meters of the marker or object. Once Deimos reaches its target, it stops, signals its arrival through onboard LEDs, and outlines the detected object at the base station through the GUI.
We would like to thank all of our sponsors for their support. Team Mountaineers is ready and excited to compete at University Rover Challenge 2026.